Hello everyone, and welcome back to Mitchell's Physics Review. Today we will be working on Kirchhoff's rules. Let's take a look at our problem. In the circuit in the figure below, determine the following. A. The current in each resistor. B. The potential difference across the 80 ohm resistor. To start, let's draw a diagram and determine which ways our current is flowing. As you can see, I copy and pasted a picture from the diagram above. In this case, I had current W flowing upwards, current X flowing upwards, current Y flowing downwards, and current Z flowing upwards. You may ask, why did I choose these directions? I did them in correspondence with the battery terminals. Since the positive side is towards the top, I said it would flow from negative to a positive potential. In this case, since it's reversed, I said that Y would flow from this negative to positive potential. And since this one is like this one, I said that current Z would flow from that negative to positive potential. Now, for part A, to solve for the current in each resistor, we're going to have to find three equations using Kirchhoff's rules. Let's start by using current W from this point. As we move along this point, we reach our first 200 ohm resistor. It is flowing from a positive to a negative potential, or downhill, meaning it's going to lose potential. So what we're going to start with first is a negative 200 W, or resistance times the current. As we keep going along this circuit, we reach the battery. We go down from a positive potential to a negative potential, meaning once again another loss in energy. So we're going to say minus 40 for these 40 volts. However, as we approach this circuit, we're going from a negative to a positive potential, as if we're pushing uphill, meaning we're going to gain energy. So we have plus 80x, 80 being the resistance and x being the current along this branch. Then we set this equal to 0. We write this equation by using Kirchhoff's loop rule, knowing that change in V should equal 0. The loop rule shows us the conservation of energy. Now, let's start by finding a second equation. We can start from this point right here, this time looking at the X current. We're going to come upon this 80 ohm resistor, go from the positive to negative potential, meaning we're going downhill and having a drop in energy, so minus 80 times X. This time, we're going from the negative terminal to the positive terminal, meaning we are going to gain energy, so we're going to add 40 this time. And as we come around this way, we are once again going from a negative to a positive, meaning we're going uphill, once again gaining energy, this 360. Then we come upon this next resistor, and it's going from positive to negative, meaning we're going downhill and losing energy, and we're going to get 20Y. 20 being the resistance, and this time we're using Y because that is the current throughout this branch. Finally, for our last equation, we're going to start at this point right here. So we can start by traveling down, and we're going from a negative to a positive potential, giving us a plus 360. Then we come upon this resistor once again that's going from positive to negative, and that means we're going downhill, losing energy, so minus 20Y. Then as we keep traveling, we come upon this resistor, and we're going from positive to negative, once again downhill, meaning we're subtracting 70 times the current of this branch, which is Z. Then we come across this battery, and it's from a negative potential to a positive potential, as if we're going uphill, so plus 80 equals 0. As you can see, I now organized our equations, labeling them 1, 2, and 3, and I simplified them and cleaned them up. Also notice that we now have x in terms of one variable after we clean up the equations. But you may notice something a little odd. We have 4 variables or 4 different currents we're trying to solve for, but we only have 3 equations. Well, this is where we incorporate another one of Kirchhoff's rules, the junction rule. For this, I'm going to be using this point right here. Since both x and y are going to flow this way along the circuit, or towards the right in this case, we're going to have current W plus current X. We also note that current Z will be coming around and flowing this way in the current. Then they will meet at this point, and they will turn and go down this path, which is current Y. From the junction rule, we know that these 3 currents added together must equal current Y, because in these circuits there is a conservation of charge. So we can write our 4th equation that Y is equal to X plus Z plus W. Now I ask that everyone try to follow this part very closely, because we are about to brute force some algebra. So let's start with equation 2. 20 equals 4x plus 1y. First, from the junction rule, we know we can substitute in for y, giving us 20 equals 4x plus 1 times the quantity of w plus x plus c. From there, we can simplify and add like terms, and then we get to this step, where if you notice, from equation 1 up here, we're able to plug in for x. So now we have 20 is equal to 5 times the quantity of 2.5w plus 0.5 plus w plus z. Once again, we're going to distribute and simplify our equation, and we're going to get to 17.5 equals 13.5w plus z. Next, we want to write this equation in terms of z. So now we have z equals 17.5 minus 13.5w. Now, let's take a look at equation 3. 22 equals 1y plus 3.5z. Well, as we did before, we can start by substituting in for this y from our junction rule, which is 22 equals the quantity x plus w plus z plus 3.5z. Then we can combine like terms. From there, we can now substitute in for x, which we have in our first equation, to get 22 equals w plus 2.5w plus 0.5 plus 4.5z. Once again, we will be simplifying and combining like terms. Now, we can plug in for z from what we solved in equation 2 to get 21.5 equals 3.5w plus 4.5 times the quantity 17.5 minus 13.5w. Once we simplify, we get 57.25w equals 57.25. Now, I hope you have realized that we have an equation in terms of a single variable that we can solve for. So for equation 3, we're going to say 57.25 equals to 57.25w means w is just equal to 1. Now we back substitute. Knowing w, we can find x, because our x equation is only in terms of the single variable w. So we take the equation x equals 2.5w plus 0.5, plug in the 1, and we get x is equal to 3. Now 2. Z equals to 17.5 minus 13.5W. Once again, we can back substitute in this W and get Z is equal to 4. Now, equation 4. From the junction rule, we can finally solve for Y now that we know X, W, and Z. We can plug in the three now known quantities and we get Y is equal to -8. But why is it -8 exactly? Because 3 plus 4 plus 1 definitely is a positive number. Well, why is it -8? Because we go back to the conservation of charge. Our three currents are all flowing upwards. So the one flowing downwards in the opposite direction must be negative, and it must be equal to these three currents so that the overall current comes out, so that the whole change in current equals 0. Like we said in the junction rule, the conservation of energy. Finally, we get to part B, which I hope seems like a walk in the park after that monstrous problem of part A. Part B is asking us to find the potential difference across the 80 ohm resistor. Well, we know that the 80 ohm resistor is right here, and the current flowing through it is current X. So we can use a simple equation this time with Ohm's law. I equals change in V over R, where we're going to isolate the change in V. We're going to use I sub X in this case, or the X current, times the known resistance. We can plug in 3, which we found in the prior problem, and 80, which is given to us, to get that the change in V equals 240 volts. Definitely not ohms. Thank you so much for spending all of this time for me. I'd like to just go over a couple reflections on what I have learned and what I struggled with in this problem. Personally, I struggled a lot with finding the directions of currents, but I did learn there are a couple tips and tricks to that. Even if you choose the wrong direction at first, as long as you stay consistent within your problem, you will still receive the same value, just a negative current. That means we can just absolute value it to find the actual current. So make sure, even if you see a negative current, that you stayed consistent so that you know you still can have the right answer. I also struggled with where to find equation 4 by using the junction rule. And then I remembered, whenever we have a lot of variables, there's always that one equation that you're just probably forgetting about that you got to pull out from the back of your mind just so you remember what you can substitute in. I learned a lot this video, and I hope you did too. Thank you for watching. Have a great day.